Thank you very much for tuning into my ozone channel. This channel is on ozone technology course. We are now introducing session 13, which will discuss the principles of Advanced Oxidation Process, or AOP, and its applications. You might have seen this chart or table before when we discuss ORPs. Now I have to bring it back again just to use it in this context. You will find the fluoride has got the highest ORP, then comes the hydroxide free radical, following which is atomic oxygen, which is an oxygen radical that is produced during a reaction where oxygen is produced. Then comes ozone, and following them the hydrogen peroxide, and you will notice chlorine as second last, and last being oxygen. Atomic oxygen, which is number 3 on the list, is a very active radical, but is available only in the middle of chemical reactions, and its availability is very momentary. Hydroxide radicals, however, are generated when the ozone is applied in an alkaline environment, generally in a pH of greater than 8. There are also other methods of producing the hydroxide free radical besides ozone. If, for example, ozone is passed through UV, hydroxide free radical can be formed. If in an ozonated solution, hydrogen peroxide is added, you will also form hydroxide free radical. There are other methods like electro-oxidation, photocatalysis, sonolysis, gamma radiation, and ozone and activated carbon. All these can be used to generate hydroxide free radicals. Light driven by AOP can be used for removal of contaminants in air pollution. Liquids driven AOP is used for reactions in liquids, and where there are problems with pH and other chemicals in the reaction liquid, AOP can be generated through ozone, UV, or ozone hydroxide. Ozone is active as a biocide only when the medium in the application has a pH below 8. Effectiveness will be shown when the redox potential is above 700 millivolts. When ozone is bubbled through water, you will note the redox potential increases as more and more ozone dissolves. It is also note that ozone is more soluble than oxygen in water. Ozone is more soluble in salt water than in water. We will be dealing with this when we learn on ionic potentials. At pH above 8, ozone is converted to hydroxide free radicals, and the free radicals are extremely active with half-life in nanoseconds. It is too fast acting to kill bacteria, and it has been noted that when hydroxide free radicals are formed, the redox potential decreases. Because hydroxide free radical is so very active, it is the most reactive substance after fluorine. It's used in a chemical oxidation processes in the industry. As you see, chlorine is far less oxidizing than ozone. How is hydroxide free radical created with ozone? Well, we can pass ozone through a catalyst such as carbon, activated carbon, or titanium dioxide or UV. You also can pass ozone through an alkaline solution above pH 8. And what happens to ozone when it is converted to hydroxide free radical? Well, it eventually reverts to oxygen. The question now is, why is hydroxide free radical so active? See, ozone is already in a very high energy state, and it will tend to dissociate at the slightest opportunity in the presence of alkali and converts to intermediate hydroxide free radical. All intermediates are extremely active and is part of a reaction and have very short half-life that makes a radical very, very active and unstable. And therefore, it immediately releases the energy to the reactant at the first opportunity. The half-life is less than 10 to the power of minus 9 seconds and usually unsuitable as a biocide. As an emphasis, the AOPs are generated by a variety of radical reactions that involve combinations of chemical agents. Ozone, hydrogen peroxide, or ozone with transition metals, or metal oxides, and auxiliary energy sources such as UV, radiation, electronic current, gamma radiation, and ultrasound. Examples of AOP include ozone hydrogen peroxide combination, ozone UV combination, ozone hydrogen peroxide UV combination, hydroxide peroxide, hydrogen peroxide UV combination, the Fenton reactions and hydrogen peroxide, photo and electro-Fenton chelating agents, assisted Fenton and photo-Fenton heterogeneous photo-oxidation using titanium dioxide. It may be a bit complicated or difficult for those who don't know much about chemistry, but if you are interested, the internet is always available for you to go further into it. This is the diagram of using pyrolysis with ozone to provide hydroxide free radicals. The ozone is taken through an absorption column, and it is directed into the generator in a bar where the ultrasound is effected. Then the ozone is converted to free radical, and off gas, particularly oxygen, is liberated. This is another diagram using ultrasound to produce the free radical. If you notice that the ozone can be passed directly into the ultrasonic transducer, which produces the sound, and we will be able to use that water, which will contain the hydroxide free radicals, and any off gas is released into the atmosphere. Because this process is also exothermic and releases a lot of energy, they will have to use a cooling setup to cool the heat generated. The AOP process is very complex and very highly technical, so that this session referred only to the principles and generally how it is applied. The AOP is applied in many chemical industries during the manufacturing process. With the ozone technology, we can apply for very difficult chemical oxidations that are normally very slow or difficult in the normal oxidation reduction reactions. The hydroxyl free radical has very short half-life in the region of 10 to the power of 9 seconds, and the free radical is so very reactive that it would rapidly react and oxidize in most chemical oxidation processes. I list some of the common applications of AOP. They use it to break down pesticides. They can use it for destruction of mutagenic, carcinogenic, genotoxic drugs and the metabolites in the sewer treatment. They remove formaldehyde, phenol in wastewater systems, and they are used in oxidation of very difficult chemicals that require very high potentials. We can also use this for the treatment of dye effluents and remove the dye coloration. We have come to the end of this session 13. The next session 14 will be on the properties of ozone. If you are new to this session, please refer to sessions 1 to 2, which will give you the details of the program, and sessions 3 to 12, which will be the details on each of the sessions of the course. If you like this presentation, please click the like icon and subscribe icon if you want to be notified of the next session. Thank you once again and have a good day.